Hello, welcome back to STEM with Sid, and today I'll be going over topic 1.4, continuity and one-sided limits. So in order for a function to be continuous, there must be three requirements, there are three requirements for the function to be continuous. And first one is f of c exists, so c being any value, so you can check if f of c exists, you satisfied one condition for the function to be continuous at x equals c. Then there's another condition, limit of f of x as x approaches c must exist as well. And then finally, the limit of f of x as x approaches c must equal f of c. So for an example, you have 1 over x, which I've graphed here. As you can see here, it is continuous. There are points here, and there are limits, right, that exist, and they equal those points. However, at x equals 0, well, 1 over 0 is undefined, right? The right side goes to positive infinity, left side goes to negative infinity, right? That's something I can go over right now as well. The one-sided limits. So when you draw, when you do limits, right? Limit of f of x. Let's say f of x is 1 over x, right? X approaches 0 from the right. Then it's going from the right, and we can say it's to infinity. The whole limit doesn't exist because, as I said before, the left limit and the right limit must exist in order for the limit to exist, right? However, if you go from the right, it's infinity, right? And if you go from the left, denoted by the minus sign, we can say it is negative infinity. But either way, these don't exist, right? And the value doesn't exist. So f of x, in this example, is not continuous. It is continuous at every value except x equals c. And another thing is if you're looking at a certain value of, let's say, f of c, right, and g of c, right, then if both of those functions, like f of x is continuous at all values, right, and g of x is continuous at all values, then bf, which is a scalar, f plus or minus g, f times g, or f divided by g, or even f of g of x, a composite function, all of those will be continuous, and even at x equal value of c, if that's the case for f of x and g of x, of course, right? So if it's continuous at all values, then all of this work, okay? All of those will also be continuous. Lastly, I'll go over the intermediate value theorem. So for the intermediate value theorem, basically, if f is continuous, so there's three, requirements here. If f is continuous on f of a, so let's say let me just reword this here. If f is continuous on a, b, f of a doesn't equal f of b, and k, or let's say f of a is less than k, so there's a k in between, there must be a c between a and b such that f of c equals k. Pretty much what this says is if there's a function f continuous, a continuous function, no discontinuities at all, on a to b, right? That's the interval. And f of a does not equal f of b, okay? So the f of a does not equal f of b, and f is continuous, right? And there's a k in between those two y values. There must be an x value, or c, between a and b, such that f of c equals k. So just to show you what that looks like graphically, is if you have this, let's say a graph, let's say my a is here, my a is here, even though that would be 0 in this case. Actually, let me change that, because that will be 0 in this case. Let's make this a, let's make this b. And f of a can't equal f of b, so let's just say f of a is here, and let's say f of b is here. So you can connect the dots however you want for the graph, but let's just say our graph goes like that. There must be, let's say there must be a k in between, right? Or f of c, right? There must be a k in between. So, well, that could be here. If I draw this correctly, that could be this value here. K is between f of a and f of b. Since it's continuous, there must be that value, which is c in this case, such that f of c equals k. Thank you for listening to my video.